All right, now we're recording on both. Were there any questions about the homework from last night? We can kind of get started on that if we want. I know I said I was going to send out a quiz. Didn't quite get around to that. Cool, 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 cool. All right, I guess we'll just hang out for a little bit longer. Give people a few more minutes. Um, oh yeah, you should have seen that announcement about the tests. Turns out everybody's got everybody's got different schedules. There's a group of about 20 people who could take it at 5 o'clock, but I think there are enough things built in that I'm just going to make the test open. Oh, question about 105A. Yeah, sure. Um, I'm just going to make the test open so you can start it anywhere from 7 a.m. to midnight, really. So in theory, at you could start it at 11:59 p.m. on the day of the test, and you would still get your 45 minutes to take the test. But obviously, that's probably not the best way to go. Let's see. Swap here over to the iPad. Fortunately, there's enough space here that we can do it right here. Yeah, so ethylene glycol has a density of 1.1 grams per cubic centimeter. What is the mass in grams of 387 milliliters of ethylene glycol? Did you have like a specific question for this one?
Uh, Actually, I just wanted to sort of see it.
Sure. Yeah. Yeah, we can work it out. So, again, let's use the sort of solution diagram method here, right? So we'll start with the stuff that we're given. We have 387 mils. I'm going to abbreviate this. And then we're also given 1.11 grams per cubic centimeter. Um, and sort of the key thing here is that, right, we need to convert first our 387 milliliters, and we know 387 milliliters is a volume. So your first step would be to convert milliliters into the units for density here. So we'll convert milliliters into cubic centimeters. And then from cubic centimeters, then now we'll use our density equation, or our density, well, not density equation, our density as a conversion factor. And we would see the mass in grams, right? So then we're going to end up with grams here. And we can see that we have cubic centimeters on the denominator and grams on the numerator. Grams is what we're looking for, so we're going to put grams on top, and we're going to put cubic centimeters on the bottom, because that is the unit that we have here, because we want those to cancel. So we'll say 1.11 grams per centimeter cubed, or cubic centimeters. And then from there, right, we need our conversion factor from milliliters to cubic centimeters. That one's actually, whoops, that's not what I wanted. That one's actually really easy. This is probably an easy one to remember. 1 milliliter is 1 cubic centimeter. It's the same. It's basically the same. It's just a different unit. So we're going from milliliters to cubic centimeters. So we'll put 1 milliliter on the bottom, and then we'll have 1 centimeter cubed or cubic centimeter on top. And so you can see if we go through here, and our milliliters cancel, then our cubic centimeters cancel, and we will end up with grams. Does that help?
Yeah, I really like converting stuff, but yeah, seeing that again really helps. I
Mm-hmm.
think I got confused on the cubic centimeter squared.
Yeah, yeah, that can really throw you off. It can be hard to identify those units and kind of which units you can convert into other units. hopefully that... Can you guys hear the weed whacker? Or what is that? Leaf blower. Hopefully that doesn't go on for too long. Doesn't look like it's too loud. Let me see if I can't. Nope, noise removal is already maxed out. Yeah, are there any other questions? Sorry. It's loud for me. All right then. Guess we will get started. Just check here before. I think I saw a couple people actually show up in the other Zoom meeting, but I will be doing a new link every day, um, and that'll let them be named on Zoom. So when you go to look at them on Zoom, they'll have the right names. And those Zoom links will be available much faster than the YouTube ones, but they're a lot lower quality, and I can't put chapters in them. All right, so today we're going to be talking about matter and energy. We're going to talk about what things are and what makes them do. Um, Really, everything in your room, everything is made of matter. Literally, everything is made of matter. Even dark matter, which we don't know what it is made of some kind of matter. Um, and different kinds of matter are related to the differences between the molecules and the atoms that compose the matter. Right? So, water is a different kind of matter than my shirt or the computer monitor. And a lot of what this chapter is putting things into categories. So how can we categorize matter to use it in different ways and to identify it and sort of group things? So kind of keep that in mind. We're creating groups here. I like this shirt. Matter is defined as anything that occupies space and has mass. So you occupy space, you have mass, you matter. And some types of matter are easily visible, obviously clothing, water, everything that we have around us. Other types of matter, and I guess I'll write down some examples here. Water. I'm just going to use water a lot as an example. Your calculator, clothes. But there are other types of matter that are impossible to see without magnification. So if you get down to a really, really small level, right, dust, unless you're looking really closely, microbes, like bacteria. We've heard a lot about the size of viruses. You can't see viruses with your naked eye, but they exist, and they're made of matter. They have mass, and they occupy space, even though it's not a lot of space or mass. So what is matter? Matter may appear smooth and continuous, but actually it is not. Matter is composed of atoms. Atoms are, and we talked about this a little bit, they're submicroscopic particles. So even with a high power optical microscope, you cannot see atoms. You need to shoot electron beams at atoms and look at the reflections of those electron beams to pick up where the atoms actually are. We'll see a picture here in a second. And these are the fundamental building blocks of matter. So you can have individual atoms. An example would be like helium and oxygen are actually form diatoms. So it's two oxygen atoms bound together. But you can get individual atoms, or atoms can bond together to form molecules. Things like caffeine, right? Caffeine is a molecule that we're all familiar with. Is made up of several atoms. And so a molecule is defined as two or more atoms joined to one another in specific geometric arrangements. For example, we talked about water, right? And so we have water, we have our oxygen, and I'm going to write it like this, right? So we have oxygen and we have two hydrogens. And this is a specific geometric arrangement. It would not be correct to write water as a linear molecule. Although those are the correct bonds, it's not the correct shape of it. And that shape is very important. as we talked about, because if we had linear water, then water would be a gas at room temperature, and life as we know it could not exist. So here's a sort of a cartoon of an aluminum can, right? All matter is ultimately composed of atoms. In some substances, the atoms exist as independent particles. In an aluminum can, however, they are all closely packed together. You can kind of think of them like marbles. Um, in something like water, however, right, the atoms are sort of floating around. They're able to move around each other. In air, they're even more spread apart, and we'll talk about that too. In other substances, several atoms bond together in well-defined structures called molecules. So this is an example here: isopropyl alcohol, right? So you got 3 carbon atoms, and you've got like 6 hydrogen atoms, and then an oxygen atom, all bound together in a specific proportion, and that proportion is very important. So here's a picture of, like I was talking about, right? We can shoot beams of electrons at atoms and get an idea of what they look like, and this is that technology. It's called a scanning tunneling microscope, and it creates an image by scanning a surface with a tip of atomic dimensions, so like a single atom, and it can distinguish the individual atoms being seen as blue bumps in this image, whereas the atoms are actually more like this previous image where they're more spherical. We use scanning tunneling microscopes to do things like image DNA. So DNA is like a. Let's see if I can draw. Um, DNA is a double helix. Kind of gets this shape, and you can sort of see that here, starting up at the top. Is there a question? Just an unmuted microphone. Right, so you can kind of see the DNA strands in there. So, sort of the most general classification of matter, right? We're taking all of matter, which is just way too much to deal with at once, and we're putting them into categories. So, our first categories that we're going to talk about are ones that we're all familiar with: solid, liquid, and gas. And of course, the easiest example of a substance that does all three of those and is very familiar to us is water, right? So we can freeze water to make ice cubes, which are solids. Liquid water is liquid, and when we heat water up, it becomes a gas, right? When we boil, if you're going to make pasta, right, you got to boil your water. Well, that boiling is actually the liquid water turning into a gas. And the defining properties of these come from how closely the atoms are spaced together. So in the solid state, the atoms or molecules of whatever the solid may be are closely packed together and have no room to move around each other. They vibrate, they oscillate sort of in their own space, but they don't leave that space. They don't move around each other. And because you've got all of these atoms locked together, unable to move, that's what gives solids their fixed volume and rigid shape. And so we'll see we'll move on to the next one here. No, still talking about solids.
I have a quick question.
Yeah.
So obviously we can tell like in everyday life the difference between solid, liquid, and a gas. But scientifically, is there a way that you particularly define how close those atoms are together and what space the difference is between each state?
That's a really
Like,
good question.
yeah, do you understand what I'm saying? Where's the line
Is there a
scientifically? Where do we draw
deeper.
it?
Right, so it's like if they were, if they're less than 12 nanometers apart, is that a
Yeah,
solid? I
exactly.
I don't think there is. There's not one all encompassing, this makes a solid or this makes a liquid. I mean, when we talk about gases, we actually sort of, in the sort of, how do I say this? In the simplest model of gases, They are like infinitely far apart. So they're so far apart that they have no interactions with each other. They'll whiz around and occasionally they bump into each other. That's a later chapter. But yeah, so no, there's not one set definition. And actually, this next slide will kind of explain why that is.
Gotcha.
So yeah, good question. Very good question, though. I would Google it. And if you get it, if you do find an answer for that, my intuition would be no. I haven't heard of something like that. But if you find something, post it in the Discord.
Yeah, we'll do.
Yeah. So part of the reason I don't think there is a set definition for all solids, or yeah, for all solids or all liquids, is in solids we have two different types of solids, right? So again, we've taken, or I'll write this down here, right? So we have solids, and then from solids we can make this sort of tree, and we have crystalline solids, and we have amorphous solids. And so the crystalline solids are things like salt. Salt is the easiest example of a crystal, or quartz. Even things like, the things that you think of as crystals, amethyst, diamonds, those have a crystal structure. And so in those forms, the distances between each atom is very definite because they have this, what we call a long-range repeating order. So if you were to somehow zoom in, maybe with the scanning tunneling microscope, if you were to zoom in on one portion of a diamond and then, scroll way over to another portion of the diamond, they would look identical. And so going from place to place, you're going to see the exact same pattern. And you can see how these are sort of stacked together, locked in here, right? You can see the order in these atoms. In an amorphous solid, which is actually more of the solids that we deal with on a daily basis, there's no set structure. The atoms are close, they're stuck together, they're not moving around each other, but there's no pattern to them. And partly this happens, so this is an example of maybe an amorphous solid made of, right, there's no pattern here. Some of them are like obscuring others. It's all fairly messy. And this is an example of maybe what we'll call a pure substance, where it's made of a single type of atom. But for almost everything, you've got mixtures. So it's not just one type of atom. You'll have some long atoms, you'll have some short atoms. Plastics, for example, if you were to ever look up what is in plastic, there are things, there's the plastic itself, there's stuff called plasticizers that changes the properties. And part of the way it does that is by either letting the atoms, or the molecules in this case, stick closer together, or it forces them to be farther apart. And that gives you different properties for those materials. So moving on to the liquid state. In liquid matter, atoms or molecules are close to each other, but are free to move around and by each other. So liquids have a fixed volume, again, because I hesitate to say this because I don't want to confuse you. So think of like your amorphous solid here, right? You've got all these things, they're packed together, and in amorphous solid, they're fixed. But imagine if you gave them a little bit of space to move around. They can slide around each other now, they can change spots. It's like when you pour water on a table, right? Water is liquid. Those molecules, they want to stay touching each other, but because they have room to move around, they'll spread out. And so because of this, liquids have a fixed volume. Because those atoms are already touching each other, you can't force them closer together within reason. If you try hard enough, you can, but then it becomes a solid. But those atoms are already touching each other, so you can't force them closer together. So they have a fixed volume, but because they move around each other, they are free to change their shape, and they will take the shape of their container. Right? You pour water into a cup, it fills that cup. Right, yeah, because they're free to move around each other. And we don't have like an amorphous or crystalline. There's not another sort of category for liquids. For gaseous matter now, we've taken those atoms and they're no longer touching each other. Like I said, they're essentially, for all practical purposes, infinitely far apart. They're flying around, they're moving, they each do their own thing, And in fact, according to the ideal gas principles or ideal gas law, they fly in straight lines until they hit something, and then just like um, balls in a pool table, they bounce off just like balls in a pool table, but in 3 dimensions. So in our gaseous matter, our atoms or molecules are separated by large distances. They're free to move by one another. Um, and because there's no actual contact between those atoms, that's why gases are compressible. That's why you can fill a balloon. That's why you can, well, I don't know if any of you use an AeroPress, but in AeroPress, you're compressing gases, creating pressure, and forcing your water out. Yeah, and then gases always assume the shape and volume of their container. Um, One way you can kind of think about this is when you cook. When you cook things like garlic or onions or other stuff like curry, those smells are gases. And that's why when you cook those things, the gases come out of the pan and then they will spread out and fill up the house. And actually, eventually, they'll spread out to fill every part of the house evenly. Yeah, so gases, they're free to move around each other and they are compressible. And they fill the shape and volume of their containers. And here we have just a table that probably very useful table. If you want to come back, you want to review these things, especially while doing the homework. You'll find this table in the book as well. Just summarizing sort of all of these different properties of your solids, liquids, and gases. Now, so again, we've taken all of matter and we've broken it down into solids, liquids, gases. For solids, we now have, oh, actually, I should do this right here. We'll zoom in real quick. So we have all of matter, and now we've broken this down and we have solids, we have liquids, and we have gases. And then from solids, we can go one step further and we can say they're either crystalline or amorphous. And this is, in some ways now, we're going into sort of a separate categorization. But we're going to categorize these things sort of again. So now for solids, liquids, and gases, we can either have pure substances, which is composed of only one type of atom or molecule, or we can have mixtures. And our mixtures are composed of 2 or more different types of atoms or molecules, combined in variable proportions. Right, so here's the sort of classification tree. And this is going to be another one of those things that you're going to want to refer back to. I will, obviously, I'll post these slides. I think, I uploaded the slides from yesterday, but I didn't link them yet. So you can see we break matter down into our pure substances. These are the things that are only either one type of element, or one type of atom, or one type of molecule. And so we break those down even further. If we have only one type of element, so one type of atom, then we go into elements. If we have one type of molecule, those are compounds. And on the other side for mixtures, right, so now we've got multiple types of atoms or molecules in various proportions. We can now break those further down into homogeneous, meaning that the consistency or the distribution of atoms and molecules is the same throughout. There's a lot of things that we know as being homogeneous, right? Like milk, right? Milk's not just water. It's got a lot of other stuff in there, milk fats. Here, for example, there's tea, right? You're not going to drink one part of the tea and then drink another part of the tea that tastes different. If you go to Starbucks, however, and you order like a caramel macchiato or something, well, usually they end up having too much syrup at the bottom. So you could say that that is a heterogeneous mixture, because when you're drinking it at the top, you've got, maybe it tastes more like coffee, less like caramel, and by the time you get down to those last dregs at the bottom of the cup, it's almost all caramel. Another good example would be here, if you've ever mixed oil and water. I mean, you could go, I mean, don't go to your kitchen right now, but you go to your kitchen today, grab some oil, olive oil, canola oil, whatever, pour it in a cup, pour some water in a cup. They're going to separate. And that is an example of a heterogeneous mixture, right? So the consistency is not the same throughout. We talk about elements. The most obvious place is the periodic table. It's the periodic table of the elements. And so pure substances cannot be broken down into simpler substances. There's no chemical transformation that can decompose an element into simpler substances. So like pure oxygen, right? It's only oxygen atoms. Only oxygen atoms. And then it does form it's like this. They form, wow, I'm blanking on the word. They're diatomic. So there's actually two oxygen atoms. But because it's only oxygen, that's still an element, right? It's only one type. We can't break this down into something other than oxygen. And that's why we have all the elements listed on the periodic table. And then there's one in the front cover of the book, and there's the alphabetical order on the inside back cover. A compound, on the other hand, is a pure substance composed of two or more elements in fixed, definite proportions. I don't know if you remember yesterday when we were talking early on, there was the example of breaking down water. We broke down water into oxygen and hydrogen, and that always comes out in the same ratio, right? It was about 8 to 1, right? So there were, and really actually the ratio is 2 to 1. It was by mass, it was 8 to 1. But if we have a water molecule, right, we have our oxygen. I'll use red for hydrogen. Let me label these. Oh, that wasn't very good. Hydrogen. And this is oxygen. And water is always in this same proportion. There's always 2 hydrogen atoms and 1 oxygen atom. And so that would be a pure substance, but it would be a compound. And compounds are far more common than pure elements. Most of the time, almost everything we interact with is going to be a compound. And they can be decomposed into simpler substances. So a mixture, and then to take it from a compound to a mixture is composed of different substances that are not chemically united, but simply mixed together. It would be kind of like if you took, if you made stir fry. Stir fry is kind of the example that comes to my mind, right? It's like stir fry, right? So if you're adding in broccoli, you're adding in corn, or like little baby corns, you're adding in carrots, all of these different things. They're not chemically bonded together. They're just physically mixed together. And in a similar way, when you make something like, or when you add sugar to water, the sugar is not chemically binding to the water. It's just mixing in. One of the important things about mixtures is that they can be separated physically, and their proportions can vary, right? So we can have a mixture with a little bit of sugar. I should draw more, right? We could have this, and we could have 1 gram of sugar, or we could have the same amount of water, and we could have 10 grams of sugar. And those are both still mixtures. The proportions don't change whether or not it's a mixture. Air and seawater are both mixtures, right? In air, it's mostly nitrogen, oxygen, and then there's also argon and helium. There will be carbon dioxide. Also, anything that you smell is part of that mixture. Seawater is going to have salt in it. It's going to have different kinds of salt. It's also going to be mostly water. And so both of those are mixtures, right? Because you could add more salt to the water, and it's still a mixture. It's not a fixed proportion. So back in our previous sort of table flowchart of how we're categorizing matter, mixtures then can be further broken down into homogeneous mixtures or heterogeneous mixtures. So a homogeneous mixture has the same composition throughout. That would be like your coffee, just black coffee. That's a mixture. It's got water, it's got your coffee, however you make it, but you can make it stronger, you can make it less strong. So it's a mixture. Um, Same throughout. The easy one for a heterogeneous mixture, right? Oil and water. It's so common it's a saying. It
So
doesn't mix.
heterogeneous is anything that separates.
It's anything that separates. It's anything that doesn't have a constant. So the other example would be like my caramel macchiato. So you have your caramel macchiato, and then you've got like that caramel at the bottom.
Okay.
So, don't get confused here. Black coffee, right? We've got black coffee here. Or if you were to mix this, really well, then it could be homogeneous. But if you don't mix it, it's heterogeneous. Does that make sense?
So what makes the difference between it being a heterogeneous mixture and two separate things that are just touching each other? Because like oil and water, to me, they're not really mixed. They're just two separate substances that are touching each other.
Yeah, that's actually a good point. I think
If you then emulsify your oil and water, is that can now considered homogeneous,
if you used an emulsifier, yeah.
like a
Yeah,
whisk
so
or
you could
something?
make oil and water mix if you use the right compounds. And that's what there's, a whole field of formulation chemistry that is getting oil and water to mix. So, yeah. I would say yeah, you make a good point with the oil and water. They are two things touching each other, but I think because they're occupying the same sort of vessel, you could even, say, okay, it's oil, water, but we shake it up a little bit. If you do that, you're going to find that, yeah, the oil and water, eventually they'll settle back out. Another example of a heterogeneous mixture, um, actually, well, soup.
Okay,
So
so
if you had
so is
soup,
it homogeneous if it won't settle back out, but it's heterogeneous if it will settle back out? That kind of a
yeah,
like
and
what?
that's actually getting into a further thing that I don't think we talk about in this class. There are colloids and suspensions. So milk is a colloid. This is not something that you'll be tested on, but milk is a colloid. So um, there are oils and fats in milk, but they're emulsified. Those won't fall back out, and I'd call that homogeneous. If it does settle back out, I'd say that's heterogeneous. Another example, maybe that's less ambiguous, would be like if you had a beef stew, right? So you're gonna have your chunks. You're gonna have like chunks of things, carrots and chunks of beef in the beef stew, all mixed together in the same bowl. That would be heterogeneous. Maybe that's a better example.
Yeah, I think that does help.
Yeah, because the oil and water. But see, so that's how too. The oil and water is kind of like your beef stew, in that they're not. You wouldn't say that it's like blended in. That the like vegetables and stuff they're not blended into the soup. They're just kind of occupying the same space. You could say that they're just touching, but they're sort of part of the same vessel, I guess.
Yeah, that makes sense. Thank you.
Yeah. So these are they're categories, right? They're things to help us break things down, and deal with different things differently. And I think right here. Oh no, we're gonna just talk about classifying some matter. So yeah, see, so let's go ahead. I mean, if you want to say it out loud, you can say it out loud or put it in the chat. Let's classify these um, as mercury in a thermometer. Is that a mixture or pure substance?
An element,
Pure substance.
element.
Mm-hmm. Pure substance and an element. Right. Exhaled air. Pure substance or mixture?
That's a mixture.
Mixture.
Mm-hmm. Mixture, right? Because you're breathing out oxygen. There's a little bit of oxygen in there. If you've got bad breath, if you haven't brushed your teeth, there's going to be other stuff mixed in there. So it's going to be a mixture. Now, would that be homogeneous or heterogeneous?
Homogeneous.
Homogeneous. Actually, well, it doesn't really matter. It's kind of a semantic thing. Homogeneous and homogeneous are actually different words. My wife and I got into this and started Googling it. I'm not exactly sure why, but it is actually a different word. Sorry, that's a tangent. So chicken noodle soup. Substance or mixture?
Mixture.
Mixture.
Right, mixture. Like we just talked about, a heterogeneous mixture. And then table sugar. Might be a little harder.
What's a compound?
Mm-hmm. Yeah. A pure substance, but a compound. Oh, actually, here, let me write these down for those who will just look at the slides. So we're going to say that this is pure, and it's an element, and this is a mixture. It's homogeneous. And we're going to mixture, heterogeneous, and sugar is a pure substance. Ooh, my handwriting's bad. It was a compound.
So would water be a mixture also? I mean, if exhaled air is a mixture, would water be a mixture as well? I mean,
Yeah, good
combining.
question. So it depends on the water, right? Your tap water, really, probably more of a mixture, right? Because you're going to have, you hear about water hardness. You hear about things like nitrates being in water. So there's a lot of other stuff in water. Now, if you take that and you put it through reverse osmosis, and reverse osmosis is incredibly good at getting all of those out, then that could be a pure substance. But this is why, they're categories. They're for grouping things generally. You can get down and split hairs, yeah. And see that almost everything is going to be a mixture. Like even your table sugar, right? There's probably some other, I don't know, dust or something in there, and you can split hairs. But for this class especially, we're going to be thinking sort of at the most general level. And so if you get a question on the test and you see sugar and you're like, oh, hey, he said there's dust in sugar, so that's a mixture. That's not the answer I'm looking for. But yeah, that's a good point. Right, so let's just summarize here, right? So matter may either be a pure substance or it may be a mixture. Pure substances can be either elements or compounds. Mixtures can be either homogeneous, or heterogeneous. Mixtures may be composed of two or more elements, two or more compounds, or a combination of both. So again, I would refer back to that flow chart. If you can lock that flow chart into your mind, that's going to be easier than just trying to remember these by rote. Right. So now we're going to talk about properties of matter. So we know different matters or different types of matter intuitively by touching them, by looking at them, by feeling at them, right? You know that something is like this Altoids tin, right? You know this is made of metal, probably because you've held an Altoids tin before, but you can touch it and you feel, oh, it feels cold. And we know that metals feel cold. And we know that when you tap on it, I don't know if you could hear that, right? It makes a particular sound. And so the properties of matter are also another way that we categorize things. And we can break those properties down into physical properties, things like the Altoids tin is shiny, it's cold to the touch, it makes a particular sound when you tap on it. Those are all physical properties. Color as well, taste, smell, these things are all physical properties. And those physical properties are displayed without changing its composition, right? So I don't change this Altoids tin by looking at it. I don't change it or too much by tapping on it. I'm not changing the composition by tapping on it. I don't even change the composition if I crush it. Those are all physical properties. Chemical properties are different. So chemical properties are ones that are displayed only through changing its composition. Things like burning. Things like if you leave plastic out in the sun, right, it yellows. That's a chemical property. And that changes the plastic, because usually the plastic gets more brittle, it falls apart, it's not as strong. Mostly the ones that we'll talk about, and I'll use these examples probably, are flammability. That's the one that we're most familiar with. But there are also things like corrosiveness, acidity. So acidity is actually a measure of the number of proton ions. We'll talk about that later. Toxicity is also a chemical property.
So they're two separate things, but the chemical properties often change the physical properties, right? When you alter a
Yes.
chemical property, it all often has an impact on the physical property.
Yes. Yeah, a chemical property, right? Because we're changing the composition of the substance. So it's not the same substance that it was before, right? So that plastic is going to be one thing. It's going to have one set of physical properties. You leave it out in the sun, it turns yellow, changes color, right? It's brittle. It's changing like the physical strength because it's not the same plastic anymore. There's actually something happening with the probably UV radiation from the sun that is actually changing the composition of that plastic. So we're actually getting it. You actually have something different than you did before. Yeah, but just know that, right? So even though chemical properties do change the physical properties by changing the composition, by changing the substance, the physical properties are ones that you can observe without changing it. This maybe gets a little bit right. You might think of boiling in this example, right? So atomic or molecular composition of a substance does not change when the physical substance, or when the substance displays its physical properties. Like the boiling point of water is a physical property. But you have to think about it sort of at a compositional level, like we talked about with the, 3 states of matter, common states of matter. When you boil water, it's still water. It's just gaseous. So if it's a state change, if you're going from solid to liquid to gas or back again, those are physical changes. And those are dependent on physical properties. Because we're not changing what the substance is, we're just changing the state of that substance. So that's an example maybe where you are changing what it looks like, you're changing what it feels like, you're changing some of the physical properties, but you're not changing it chemically. Just give that a moment. Right, so when water boils, it changes from a liquid to a gas, but it's still water. When you leave that plastic out in the sun, you're breaking chemical bonds with UV radiation, and it's not the same plastic anymore. Iron rusting is another good example of a chemical property, right? Because when things rust, they do get weaker, and you can see that rust on them. But you can see here from these, I'll zoom in here, right? Our pure iron over here looks like this. When it rusts, we form iron oxide. And you're actually inserting, not just inserting, but these are chemically reacting with the iron to put oxygen in between the iron molecules, or iron atoms. And that's what changes its composition. Understanding the difference between chemical and physical properties really requires sort of an understanding of what's going on below the surface. Kind of the difference between a theory and a law, right? You got to understand why it's happening. And that's the most surefire way to get those questions right. So let's look at these examples on the Skillbuilder, right? So the explosiveness of hydrogen gas, is that a chemical or a physical property?
Chemical.
Right. Chemical property, right? So we're changing that hydrogen gas actually from hydrogen gas. We're combining it with oxygen, and it's becoming CO2 and water. The bronze color of copper. Physical or
Not
chemical?
chemical.
Physical, right?
Physical. Yeah, so it's a physical property, right? We're not changing anything about the copper. I think there's another question, but here, yeah, so this is, and I should write these down again. Chemical, physical. Let's say, though, you leave copper, right? So just like iron, if you leave copper out get it wet, leave it out in the elements, it changes color, right? It goes from a bronze copper color to a green color. Is that a chemical property or a physical property?
That's
Chemical.
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 That would be a chemical property. Yeah. Again, the shiny appearance of silver.
Physical.
Physical.
Physical property. And then the ability of dry ice to sublime or change from a solid directly into vapor.
Chemical.
Well,
Physical.
Physical property. Yeah, that one's a little trickier because you're going from dry ice as a solid straight to, well, and dry ice is carbon dioxide. So you're going from dry ice, carbon dioxide as a solid, to carbon dioxide as a gas. Yeah, so it requires sort of a little bit of knowledge about what is going on at an atomic level, right? And to tie this back to chapter 1, right, we're understanding these things now at a atomic level, and by understanding them at an atomic level, we can describe what they're going to do at sort of the macro human-sized level.
I thought you said it was physical.
Sorry. My bad. Thank you. Please catch me on that kind of thing. Because talking and writing and you know how it goes. All right, so what happens to atoms and molecules when matter changes? And this is something that we've talked about already, right? In a physical change, matter changes its appearance, but not its composition. That's the dry ice subliming, water freezing, or water melting, or ice melting, I should say. It looks different, but it's still water. In a chemical change, the matter does change its composition, right? Again, copper turning green under continued exposure to air, because it's reacting with the air. But we talked about chemical and physical properties before. Now we're talking about chemical and physical changes. Or physical changes are things like state changes. Those are definitely the most common. Another physical change would be like if you had a block of wood and you cut pieces off of that block of wood. You're physically changing the wood. The pieces that you cut off are still wood. The piece that you're cutting them off of is also wood. Alright, so the atoms that compose the matter do not change their fundamental associations, even though the matter may change its appearance. Physical change results in a different form of the same substance. Chemical changes, on the other hand, we are, again, like we've already talked about, atoms are changing their fundamental associations. So we're adding oxygen to either copper or adding oxygen to iron. That's a chemical change. That's resulting in a new substance, copper oxide or iron oxide. Matter undergoes a chemical change when it undergoes a chemical reaction. So the stuff that we have before, the substances that we have before are the reactants, and the substances present after the change are called products, right? So in iron rusting, you start with iron, undergoes a chemical change, we add oxygen, and our product then is rust. Right, so vaporization is another example of a physical change. So we push the button on a lighter without turning the flint. You're just letting out liquid butane, and it vaporizes into gaseous butane. And I'm not saying don't try this at home. Don't try this at home. Don't try this at home. You can take the butane and cup your hand and let the butane out into your hand. And the butane is actually more dense than air. And so you can hold the butane there. You can know you're holding the butane because when you do light it, it poofs up into the air. Don't try that at home. The liquid butane and the gaseous butane are both composed of butane molecules. So it's a physical change. On the other hand, as soon as you turn the flint and create a spark, then you're actually converting, right? You have a reaction. There's a chemical reaction happening. Your butane molecules are reacting with oxygen, and they form new molecules, carbon dioxide and water. And that's a chemical change. I think the next... Well, okay. I thought that there was a slide coming up next. But just to write this out in terms of a chemical reaction, right, we have butane, which, what is butane? I know it's CH4 or C4 610, C4H10. So that's, let me write this a little more neatly. So when we have butane, we have 4 carbon atoms, 10 hydrogen atoms, and we're adding oxygen. I'm not going to balance this, but then, so these are our reactants. And we're undergoing a chemical change. Delta is the sign in chemistry for heat. We add heat, and that causes it to change into CO2 plus water, which is H2O. And these would be our products. So let's classify these then. So copper metal forming a blue solution when it's dropped into colorless nitric acid. Think about what might be happening at an atomic level here. Is this a chemical or a physical change?
Chemical.
Chemical change. So yeah, copper is actually reacting with the nitric acid here and is forming a new molecule that's blue. If we a train flattening a penny placed on a railroad track, chemical or physical?
Physical.
Physical.
Yeah, physical change. Again, I need to chemical, physical. Ice melting into liquid water. We've said this one enough. A match igniting a firework.
Chemical.
Chemical. If anything's burning, if you ever burn anything, it's a chemical change. That's a surefire one. I don't think there's any time that would be wrong. So when we take our mixtures, we can take advantage of physical and chemical changes or physical and chemical properties in order to separate things. Distillation is one. You can actually, if you go out and buy the sort of glassware to do it, you can take like orange peels and you can extract out that orange zest. And what's happening here is you have a mixture of your liquids on the left over here. And as we boil those, different compounds have different boiling points, right? So water boils at 100 degrees C, but there are a lot of things that boil at higher or lower temperatures. So as you boil this mixture, whether there's water in there or not, the stuff that's lower will boil first, then maybe you'll get your water, and then later you'll get off the other stuff that boils at higher temperatures. And then you just swap this flask. You can swap this flask out at each point to get your different compounds out. Another way that we separate things, and if you make coffee, you're familiar with this one probably, is we can use filtration, right? So when you make coffee, your coffee grounds don't dissolve into the water, and we filter those out because they're physically bigger than the holes in your filter paper. And we can do this on a smaller level if you look up gas chromatography or liquid chromatography. Those are sort of doing this same thing at a very, very, or some of them are, at a smaller level. We're separating things through their physical properties. And actually that's how reverse osmosis works. Reverse osmosis has a membrane, and the holes in that membrane are only big enough for water molecules to get through. And so when you force the water up against this membrane, there's other stuff in here that's bigger. Your nitrates, your other dissolved minerals, all bigger than water. Only the water molecules get pushed through. Whoa. Oh, right. Okay, so I'll talk about the conservation of mass. There is no new matter. Matter is neither created nor destroyed in a chemical reaction. In a nuclear reaction, we actually are converting matter into energy. That's why this says there is no new matter. We have no way, or know of no way, to take energy and convert it into matter. This actually comes from Einstein's famous equation, E equals mc squared. Probably heard it over and over again, but this is mass. And this is the speed of light. And E is energy. So in a nuclear reaction, what's actually happening is the process of, in nuclear fusion, you're taking hydrogen isotopes, smashing them together, and when they bond together, some of the matter is actually converted into energy. And then you take that mass and multiply it by the speed of light squared. The speed of light, right, is like 3 times 10 to the 6 meters per second, which is incredibly fast. It's the fastest. And so you multiply that tiny amount of mass by the speed of light squared, and that creates energy. And that's why you get so much energy out of nuclear reactions. But in chemical reactions, the stuff that we're going to be doing and talking about until the very last chapter, the changes are so minute that they can be ignored. So during physical and chemical changes, the total of matter remains constant. Oh, and this is the one I was thinking of, right? So we were combining butane and oxygen, 58 grams of butane, 208 grams of oxygen, it's 266 grams. You're going to get 266 grams on the other side. And again, we talked about this, chapter 1, chapter 2. This was Antoine Lavoisier's experiment. He burned these things in sealed containers and found that there was the same amount of mass at the beginning as there was at the end. So now let's combine 12 grams of natural gas with 48 grams of oxygen. And the chemical change produces 33 grams of carbon dioxide, but how many grams of water? For this kind of problem, probably, you can write out the stuff that you have, but we're talking about a chemical change, right? So we're talking about a reaction. So we say that there's 12 grams. I'm just going to abbreviate this as natural gas plus 48 grams of oxygen, which is O2. These react together, and we know they produce 33 grams of carbon dioxide, CO2, and, so plus, how many grams of H2O? So knowing conservation of mass, you can actually just rewrite this as an equation, right? So we know that whatever is on the left side should be equal to whatever is on the right side. So we can do 12 grams plus 48 grams, because it doesn't matter what they are here. We're just trying to get, let me use an equal sign, 33 grams plus X grams, right? So a little bit of algebra. Again, if you want to brush up on your algebra, go to the back of the book. There's an appendix chapter for that. And so we'll get 60 grams on this side, and I'll just sort of skip a step here. Minus 33 grams equals X grams of H2O, which is equal to 27 grams H2O. So the amount of mass on the left side will always be equal to the amount of mass on the left side in a closed system. Right? We're always going to produce that amount. Actually, not even in a closed system. It will always be equal on the other end. But to measure it, you'd need a closed system. Now, we've talked a lot about matter. We've talked about what things are, right? We've placed them into different categories. We've talked about them as homogeneous and heterogeneous. We've talked about them, about chemical and physical properties. We've talked about chemical and physical changes. We now know what a reaction is. Energy is what makes all of these things happen. Energy is a major component of our universe, right? It's why things happen. Energy is the capacity to do work. And work is defined as the result of a force acting over a distance. And the behavior of matter is driven by energy. So understanding energy is critical to understanding chemistry, because if we understand energy, we understand the forces that are driving the chemistry. You may be familiar with the law of conservation of energy. So energy is neither created nor destroyed. Like matter, energy is conserved. So energy cannot be created out of nothing, and it does not vanish into nothing. It always goes somewhere, or comes from somewhere. The total amount of energy is constant. But there are a lot of different forms of energy, and we can transfer energy from one object to another. Kinetic energy, right, that's the energy associated with motion. Potential energy is the energy associated with position or composition. So my water bottle here, my invisible water bottle, when it's higher up, or a coffee mug, when it's higher up has more potential energy than when it's lower. We're familiar with electrical energy, which is the energy associated with the flow of electrical charge. Thermal energy, the energy associated with the random motions of atoms and molecules in matter. And chemical energy, which is a form of potential energy associated with the position of the particles that compose a chemical system. The position of the particles that compose a chemical system. So chemical energy, usually we talk about in the form of bonds between atoms, forming or breaking those bonds. And then the total energy of a sample of matter is the sum of its kinetic and its potential energy, right? So when we have a dam like this, the water on this side has a high potential energy, and the water on the other side has a low potential energy. And we can take advantage of this by flowing this water through turbines and converting that potential energy into the falling kinetic energy, and then that'll spin a turbine to create electrical energy. But the total energy of this system, right, is the kinetic plus the potential energy. When we talk about energy, the units that we use are, there's a few different units that we use, actually. There's the joule, that's the SI unit of energy. There's also the calorie, lowercase c, and that's the amount of energy required to raise the temperature, of 1 gram of water by 1 degree C. Oh, actually, sorry, hold on. All right, we'll finish this slide. We'll take a break. It's been an hour. Yeah, I want to work some breaks in here. Okay, so finish this up real quick. So it's the amount of energy required to raise the temperature of 1 gram of water by 1 degree C. Then there's also the nutritional calorie, which is what you see on the back on the nutrition facts of, whatever food you eat. Those calories are equivalent to 1,000 of the lowercase c calories. Or it's equivalent to 1 kilocalorie, right? A kilo means times 10 to the third. So it's 1,000. And kilowatt hours are used by PG&E to measure how much electricity you draw, which you may be familiar with if you pay for your own electricity. And those prices are about to go up because it's summer. I will add here, just as a little aside, you might also be familiar with milliamp hours. MAH. Milliamp hours are usually the unit that's used by phone manufacturers or mobile device manufacturers. You might have heard that, the new iPhone has only 2,500 milliamp hours or whatever it is. And that's another unit of energy. Oh, camera's going the way there. All right, so joules. Joules here just being the capital J. Okay, so let's take a little break. I would recommend go and stand outside for a couple minutes. Make sure you're standing up, stretch a little. Or if you want, try and work out this Skillbuilder exercise before I get to it. I'll turn my camera off, but I'll leave this up. And we'll meet back at 11:10. Okay. Let's see. Camera back on. All right, so let's look at the complete combustion of a small wooden match. Produces approximately 512 calories of heat. How many kilojoules are produced? So we've got another unit conversion problem, right? Conversion of energy units. We're going to start with 512 cal, lowercase c, important to note. And again, if we use our solution map, we're going to be going from cal, probably going from cal. Oh yeah, we can go straight from cal to joules. Cal, joules. Actually, let me just J for joules. And then we'll go to kilojoules. Right? So we can fill this in, 512 calories. And then our units, our conversion factor, we'll grab from this table. 1 calorie is equal to 4.184 joules. We want joules, so we'll put joules on the top, 4.184. Double check that. Yep, 184 joules. And that's 1 cal. And we can just work on this one stepwise. 5.184 times 512. So we're going to get 517.178. Let me grab this guy. We'll move him over. And now we're in joules. To go from joules to kilojoules.
I think you added that. Are we supposed
Gosh
to
darn it.
multiply?
Yeah, you're right. Just hitting the wrong buttons on my calculator. Thank you. 2. Right. Okay, so now we're going from joules to kilojoules. Remember that 1,000 joules is equal to 1 kilojoule. So we'll put 1,000 on the bottom, 1,000 joules on the bottom, in the denominator, 1 kilojoule in the numerator, and now we'll divide by 1,000.
Am I missing something? How'd you get to 2651?
Yeah, I also got a different answer.
I got 2142,208.
Same.
512. Oh, gosh. It's because I can't hit the right buttons on my calculator.
I have that problem constantly.
It's a good thing I have you guys to check for me. 2139.136. Is that what you guys got?
No.
No, I got 2142.
What
208.
I somehow hit 187 or 178 instead of 184. $512, 4.184. Okay. Should be good now.
Yeah, there we go.
Yep, that's what I got.
Sorry about that. Divide by 1,000. All right, and then only 3 significant figures, right? Kilojoules, 2.14 kilojoules. All right, moving on. If there are no questions about that, aside from me typing in the wrong stuff. So when we have physical and chemical changes are usually accompanied by energy changes. So when water evaporates, it requires energy. The water requires energy to go from a liquid state to a gas state. We'll talk about endothermic and exothermic, but that water evaporating sucks energy from its surroundings. And that's why, if you guys know what a swamp cooler is, or an evaporative cooler, those work on the principle that evaporating water requires energy. And so then the air that comes out on the other side of where that water evaporated is cooler than on the other side. Natural gas burning, we're all familiar with burning things. When you burn something, you're releasing energy. And that energy is coming actually from the breaking of bonds in between, whatever you're burning. So some of natural gas is butane. So you're taking that butane and you're ripping those bonds apart and forming new bonds that require less energy. And so we release energy. And the release of energy during a chemical reaction is like the release of energy when a weight falls to the ground. So I remember in physics being like, okay, yeah, so we've got potential energy, we drop a weight, turns into kinetic energy, and then it hits the ground. Where does that energy go? Well, it turns out that energy actually gets released as heat. This is the reason, too, when you drive, well, you're probably not driving fast enough for it to really matter. But for semi-trucks going downhill, their brakes can overheat because all of that kinetic energy has to go somewhere, and it gets transferred into the brakes in the form of heat. So disc brakes were actually a huge invention. They cool much better than drum brakes. They also don't have expansion problems like drum brakes do. But disc brakes came from Formula One, because in Formula One racing, they're going a couple hundred miles an hour around the track, and they want to take those turns as fast as possible. But they got to remove a lot of energy before they get to the turn. So disc brakes were invented as a way to dissipate that heat from braking more quickly. There was also somebody who did a lot of math. I'll post these. I think this link will work, or you can look it up. Somebody calculated how many times you would have to slap a chicken to cook it. It was a lot. And of course, the problem is you'd have to slap it without losing that heat to the surroundings. But you could theoretically slap a chicken once and cook it if you slapped it fast enough and hard enough. So energy. Oh yeah. Systems with high potential energy have a tendency to change in a way that lowers their potential energy. Objects with systems with high potential energy tend to be unstable. Again, water, right? We're all very, very familiar with water. The reason water flows from high spots to low spots is because it's trying to lower its potential energy. Some chemical substances have relatively high potential energy. Energy is concentrated in them, like TNT. Trinitrotoluene is a very unstable molecule because there's so much pent-up energy. And that's what makes it explosive. Because when those bonds do break, they do so in a way, not catalytically, but the heat released causes more TNT molecules to release their heat very, very rapidly. Right? So that trinitrotoluene exploding would be an example of an exothermic reaction. Again, a lot of chemistry comes down to these categories. So we have categories for where heat's going in a reaction. In an exothermic reaction, we're releasing heat, we're releasing energy. In an endothermic reaction, energy is absorbed. Could also talk about endothermic physical changes, right? So the endothermic physical change that we just talked about was water evaporating. Yeah, so let's look at these and identify each of the changes as exothermic or endothermic. So, right, water freezing as ice. Is that exothermic or endothermic? Take a second to think about it too, because it's not exactly intuitive. What do you have to do to the water to get it to freeze?
It has to lose its heat to the environment.
Yes. Yeah, exactly. So water freezing, the water has to lose energy, so that's an exothermic process. And we often associate we often associate exothermic with things that we could really feel the heat from, but in terms when water freezes, you need to remove that heat, so it's exothermic. Natural gas burning is also, as you might have guessed, exothermic. And then we could have C here, right? Water evaporating. Whoops. Would be endothermic. So when we talk about heat and we talk about temperature, they are related, but they are two different things. So the atoms and molecules that compose matter are in constant random motion. That motion, which, right, kinetic energy is energy associated with motion. We call that random motion of atoms and molecules thermal energy. So the temperature of a substance is a measure of its thermal energy. And the hotter an object, the greater the random motion, and the higher its temperature. I don't remember what this barefoot people on the beach example was. There's a couple things I can think of, actually, I think I know what it is. If you have a bunch of barefoot people on the beach, the higher that you raise the temperature of the beach and the sand, the faster those barefoot people are going to move. Although in that case, they'll probably move, down towards the water or off the sand. The difference between temperature and heat is that heat is the transfer or exchange of thermal energy caused by a temperature difference. So when you feel the heat of the sun, that's the sun transferring thermal energy into your skin. It's not the temperature of the sun. Heat has units of energy, right? That's what we talked about, joules and calories. For example, when a piece of cold ice is dropped into a cup of warm water, we talk about the heat being transferred from the water into the ice. We don't talk about the temperature being transferred. Temperature then, however, is the measure of the thermal energy, right? So it's not the exchange. We say that something is that temperature, that it exchanges its heat, and that its temperature has changed. We have 3 different temperature scales for talking about temperature. The Fahrenheit scale, which is the one that we're all very familiar with, right? Room temperature, about 72 degrees Fahrenheit. The Celsius scale, which is the one we most often use because it's in units that are more easily graspable. And that's based off of the temperature of water freezing and the temperature of water boiling. So room temperature on the Celsius scale is about 22 degrees Celsius. The Kelvin scale is the only absolute scale. So 0 Kelvin is absolute 0. That is where, like we talked about, temperature is the random motion of atoms and molecules. At 0 Kelvin, the atoms and molecules have stopped moving completely. So that's absolute 0. When we convert these units, when we convert from Kelvin and Celsius, it's a little bit easier because Kelvin uses the same, not degrees, it uses the same intervals as Celsius, right? So 1 Celsius, a change of 1 Celsius is the same as the change in 1 Kelvin. But Fahrenheit, the spacing actually between each degree Fahrenheit is different than that in each degree Celsius. And that is reflected in these conversion, I don't know if you're going to call them conversion factors, conversion equations, really. And so all you need is a little bit of algebra to rearrange these, and you can solve for the other. So for Kelvin, if we wanted to say, let's say we had Kelvin and we wanted to solve for Celsius, right? So it would be Kelvin minus 273.15 equals degrees Celsius. A little bit more involved for if we had Celsius and we wanted to convert to Fahrenheit. But it would be 1.8, right? Because we multiply both sides by 1.8. Calculator popped up on my screen. Nope, please stop. Hold on. Technical difficulties. So 1.8 degrees C equals, right? And then we would add 32 to both sides. So plus 32 equals degrees Fahrenheit. So if you want to go one way, you can go the other way. You just have to rearrange the equations. Oh, the other note I wanted to make is notice that Kelvin, there's no degree Kelvin. It's just Kelvin. Okay, so let's convert 358 Kelvin to Celsius. And since we've already done that, we can just grab our equation here. I will copy this. Probably don't see anything there. Right, okay, so now we have our equation. So converting from Kelvin to Celsius or to Fahrenheit is really quite easy. It's a plug and chug operation once you've done the rearrangement. So you have 358 minus 273.15 equals degrees C. And let's see if I can do this right on my calculator. 358 to 73.15. 84.85 degrees Celsius. Right, so pretty simple stuff. If we wanted then to convert from Celsius to Fahrenheit, it's a similar thing. I'm just going to come over here because I've already done the rearrangement. Again, if you're having any trouble with the algebra involved, please go check and consult the back of the book. Do a little refresher. Khan Academy is great. I would say even for this stuff, if the way that I describe things is not good enough, if it's not clicking with you, like I'm not going to be offended if you go and use Khan Academy or if you go find another video. I want you to understand it. Okay, so 1.8, right? And we're going to multiply by, I'm leaving out the units here because we're going to end up with different units. And these units don't cancel, they don't manipulate like other conversions do. 1.8 times 139 plus 32. Make sure you remember your order of operations here. If you type this in just like it is, it'll work. Right, 1.8, 139, 32. 282.2 degrees Fahrenheit. And here, I believe these conversions are exact, so you don't have to worry about using 1.8 as your lowest significant figures when you multiply here, or using 32, right? Because it's 32 with no decimal places. You would just say it's 139 and use that initial significant figures, right? So we would actually have 282 degrees Fahrenheit. Okay, so now let's convert negative 321 degrees Fahrenheit to kelvins. So you might want to do a solution map here. We don't have a conversion factor for Fahrenheit to Kelvin. If you want to do the algebra, you can create one based on the two conversion factors that we already have. But let's do our solution map. Right, so we have degrees Fahrenheit as our starting point. Then we're going to convert to degrees Celsius. And from there, we'll get Kelvin. So negative 321 degrees Fahrenheit. We want to convert that to Celsius. Let's go back over here. Whoops. I want to copy that. Oh my goodness. For him in there, and then we'll do negative 321 minus 32 divided by 1.8. Again, got to remember your order of operations. And if I did everything correctly, just double checking my work, we should have negative 196.111 repeating. Again, remember, we're going to use the significant figures from our initial number. And then we want to convert from Celsius to Kelvin. So copy there. Paste. Undo. Paste the image here. And so now we just take our negative 196.11 degrees Celsius. That's where I would write the units. And we'll add to that 273.15 to get 77.0 Kelvin, right? No degrees Kelvin, just Kelvin. Cool, cool, cool. So when we talk about heat, when we talk about substances, you might think, how much heat can something hold, right? How much can I heat up water? Like, is there a limit? Obviously, it'll boil at some point, but what about metal? How much heat can I put into metal? Or how much heat can I put into wood? All substances change temperature when they are heated, but the amount of change varies. And so we call this the heat capacity of an object. And it's the quantity of heat, usually in joules, required to change the temperature of a given amount of the substance by 1 degree C. And actually, when we say a given amount of the substance, we mean that given amount in grams. So the mass of the substance. Wait, hold on. Oh, sorry, that's the specific heat capacity. Use the specific heat capacity to find the heat capacity. I do take some argument with the way that these are named. Anyways, the specific heat capacity, on the other hand, so the heat capacity would be like if we had 100 grams of water, the amount of energy required to heat that 100 grams of water by 1 degree C would be its heat capacity. The specific heat capacity takes that mass and makes it part of the units, so that the quantity of heat required to change the temperature of 1 gram of substance by 1 degree C is the specific heat capacity. And that has units of joule per gram degree C. So it normalizes your heat capacity to 1 gram. I think we have some examples to look at, maybe. So water has a very high specific heat capacity. It has, I think, the highest of at least any pure substance. This is going to be a table. Yeah, use this table when you have homework, on the homework. Specific heat capacities. Right, I will give the specific heat capacities on exams. For example, though, okay, just making sure there was an example on the next slide. Let's say we have lead. Okay, and let's say we have, we'll make it easy. We have 100 grams of lead. What is the heat capacity of our 100 grams of lead? So we have the specific heat, and we have the amount of lead that we have. So we can actually sort of take in a shortcut here, right? So we have 0.128, and this is joules per gram degree C. Kind of like our solution map. Writing at an angle here, but I can straighten it out if my iPad will let me. So if we look at this, I'll zoom in here. All right, we're canceling out this unit of grams with the unit of grams, and so our heat capacity for our given amount of lead is going to be 0.128 times 100. Okay, I was right. 12.8 joules per degree C. So we'll need 12.8 joules to raise our 100 grams of lead by 1 degree C. And another way that you can work this out, right? So now that we have the heat capacity, let's say we want to raise the temperature of our lead by 10 degrees C. This is where, again, unit analysis or dimensional analysis. If you've been thinking about dimensional analysis, you could probably already figure out how we're going to do this. So we want to raise 10 degrees C of our lead, and we know now our heat capacity is 12.8 grams or 12.8 joules per degree C. And just by using dimensional analysis, we don't need an equation. We can multiply these together and see that we're going to need 128 joules to raise the temperature of our lead by 10 degrees C. All right, so why is it so much cooler in San Francisco? Well, a big reason is that San Francisco is surrounded by water, and that water has a very high heat capacity. So when the California sun is beating down on us all summer, in San Francisco, the water is absorbing a lot of that heat. And dirt, by comparison, land, even wood, almost anything else, has a very low heat capacity. So instead, in Fresno, the temperature of the ground is going to raise higher than the water does in San Francisco. And so things along the coast in general stay cool. San Francisco just has the added benefit of being, oh, didn't mean to do that, has the added benefit of being on a peninsula. So it's completely surrounded. So here is the equation, kind of, for what we already just did on the previous example, is we have this heat capacity equation. So the heat, right, we have mass, specific heat capacity, and our temperature change. One of the ways to remember this is Q equals MCAT, but the A is the delta, MC delta T. Where Q is the amount of heat in joules, M is the mass, C is the specific heat capacity in joules per gram degree C, and delta T is the temperature change in Celsius. And that's temperature final minus temperature initial, right? So whatever you want to end up at minus whatever you want whatever your initial temperature is. So let's say we find a penny, a pre-1982 penny, so it's made of copper, fully made of copper. How much heat is absorbed by the penny as it warms from the temperature of the snow? -5 degrees C to the temperature of your body, 37.0 degrees C. Assume the penny is pure copper and has a mass of 3.10 grams. And we'll find the heat capacity of copper in table 3.4. So let's go back to table 3.4. Copper is 0.385. I'll write that over here. 0.385 is, and it's in joules per gram degree C. Right? Well, it says the heat capacity here. This is the specific heat capacity because we have grams in the denominator. All right, so we're just going to use that equation that we had on the previous page because we want to know the amount of heat that we're producing. We can write over here too, right? We have T final is going to be 37.0 degrees C. Our T initial is -5.0 degrees C. And the mass of the penny, so M, is going to be 3.10 grams. And this is one of those things, again, dimensional analysis is key to all of this. Because if we look at now our equation, I'll do it over here, just Q equals MC, it's actually a capital C, delta T. What are our units here? Well, our specific heat capacity is joules per gram degree C, and we're going to multiply that by delta T, which is in units of degrees Celsius. and our mass, which is in units of grams. So by the end of this, we will have canceled grams with grams, degree C with degree C, and we'll end up, not by accident, with the units for heat, Q, in joules. So this is, again, one of those ways, if you know dimensional analysis, you can figure out, by looking at the units, what equations you're going to need. Although you can also pick up keywords from the word problem. Okay, so we just fill it in here, right? 3.10 grams. I'm going to run out of space. 3.10 grams times 0.385 joules per gram degree C times, in parentheses, of course, 37.0 degrees C minus a negative 5.0 degrees C. So we have a double negative here, right? So it's a positive. We'll do that first. 37 plus 5 is going to give us 42. Now, again, pay attention to significant figures. Since this is an addition, which rule are we going to use? We're going to use the fewest number of decimal places. So since we only have one decimal place, we're going to keep the significant figures of our answer, which is going to be 42. Keep switching to the eraser. 42.0, right? Because we have one decimal place. 42.0 degrees C. And then we're going to multiply that by 0.385 and 3.10. And we'll get a heat of 50.127 joules. And since we have 3 significant figures, we will round this down to 3 significant figures and get 50.1. All right. Almost there. There's just a couple more examples to work through here, and then we'll be finished up. Yeah, so yesterday went long because it was 2 chapters and the syllabus. All right, so let's say the temperature of a lead fishing weight rises from 26 degrees C to 38 degrees C as it absorbs 11.3 joules of heat. So what is the mass of the fishing weight in grams? Easy enough. Again, I mean, here you know, right, we're working with MC delta T. We're working with the specific heat equation. So we're going to write this down. Q equals MC delta T. And this is, again, algebra is an important skill for chemistry. And we'll write down what we know. T final, 38 degrees C. T initial, 26 degrees C. And we know Q this time, 11.3 joules. But what is M? And then we can get our heat capacity, specific heat capacity, from our table back here. Lead is 0.128. So C, 0.128 joules per gram degree C. When I work out these problems, I just plug everything in, solve as much as you can, and then rearrange it. Yeah. So we'll just do 11.3 joules equals M, because we don't know how many grams, but then we have 0.128 joules per gram degree C. And then our delta T, right, 38 degrees C minus 26 degrees C. Temperature final minus temperature initial. Final minus initial is a thing that comes up a lot in chemistry. So yeah, let's solve this as far as we can. Right, so 38 minus 26, easy enough, that's 12. Now we can multiply that by 0.128. Let's zoom in on this. Multiply it by 0.128 joules per gram degree C. And we can look at these units stepwise as well, right? So here we're multiplying degree C by degree C. So we're going to end up with M times 1.536 joules per gram equals 11.3 joules. And then when we divide, so when we divide both sides, right, we're going to divide them both by 1.536 joules per gram. 1.536 joules per gram. These units are going to flip because, again, algebra thing, if we do 11.3 joules, we can also do, instead of dividing, we could multiply by the inverse. So 1 gram over, sorry, was it 1.536 joules? Because then our joules cancel and we're left with grams. So 11.3, and I'm going to do it here just as divided. That was just sort of an example of another way you could do it and think about it so that your units, so you're really thinking about it in terms of units. But to just do the math here, we're going to get 7.356. I mean, we're only working with, right, we got two significant figures. This is 3, but 2 trumps 3. So we're going to end up with two significant figures, and we'll round this then up because 5 or larger we round up. 7.4 grams equals mass. Cool. All right. One last example before we call it a day. A 328 gram sample of water absorbs 5.78 times 10 to the 3 joules of heat. Find the change in temperature for the water. If the water is initially at 25 degrees C, what is its final temperature? Again, when we get problems like this, look for clues for what equations you want to use, right? We're talking about initial and final temperatures. That should be a hint. Also, when we're given, also if you're given all of the units for an equation, it kind of, requires you to know the equation, but you should know the equation. If you're given, grams, joules, degrees C, you probably think, especially at this point where we've only got one equation, this is the one to use. So right over here, Q equals M, C, delta T. And then let's write down what we know. We have M this time, 328 grams. We have heat, Q, as 5.78 times 10 to the 3 joules. And we have T initial as 25 degrees, or I should say 25.0 degrees C. We're looking for T final, and we know that the specific heat capacity of water is 4.184. That's probably one. I will give you all the specific heat capacities that you need, but that's probably the one that you will end up memorizing, whether on purpose or by accident, or by osmosis. Okay, so again, with a lot of these problems, you just plug in what you're given, and then use algebra to solve for what you don't have. So we'll do, again, 5.78 times 10 to the 3 is equal to 328 and times 4.184. Oh, committed a cardinal sin. Left out units. Here we go. Okay. Joules per gram degree C. Running out of space. Times T final, which we don't know, minus our T initial, which is 25.0 degrees C. So a little bit more algebra involved here. Not going to get too hairy because we'll do this first, right? We'll tackle these guys first. 328 times 4.184. It's going to give us 1372.352. And then I'm going to take 5.781 or 5.78 times 10 to the 3. And right, so what are our units end up here? Right, we cancel out grams to get joules per degree C. Oh, I left out units over here too, and nobody said anything? Nobody said anything. So now we'll do 5.78. This is where you want that E button on your calculator. E means times 10 to, because you can just do 5.78 E3 divided by second answer. And we're going to get 4.21 17.
Is it okay if we just write, instead of 5.78 times 10 to the third, can we just write 5780 and calculate it like that instead of using the E function and all that? I mean, would that be okay, like on our homework and on test and et cetera?
What do you mean by, so if you wanted to write 5.
So instead of writing like you did with the 10 to the third, if I have it on my paper here, I already wrote it down, 5780 joules.
Oh.
I just took it out of scientific notation. I mean, is that okay to do?
Yeah. If you put that, remember, it's mostly because of the, right, then there's, if you put a decimal place, then there's not the implied decimal place, there's not the ambiguous number of significant figures. Okay. Oh, actually, so if you put the decimal place there, then you've got the wrong number of significant figures, so it's ambiguous. So if you were to write, 5, 7, 8, if you're doing it on your homework, I would want as an answer in scientific notation. If you wanted to write 5.78 E3, I would accept that. When you're working out problems like this, it's mostly just to keep track of what your significant figures are. Because here, right, it's ambiguous. But if I do 5780 and put the decimal place, that's the wrong number of significant figures.
Yeah, then we got 4.
Because this shouldn't be a significant figure.
Yeah.
But if you want for shorthand, especially if you're typing in homeworks, the tests will be, that's all multiple choice. So, and I'm not going to be able to check your work anyway.
Okay.
I don't remember if I made that a requirement to upload the work. But I'll have to think about that one. Right. So for when you're doing the work, it's mostly to keep track of the significant figures. If you want to write 5780 when you're doing the calculations, I'm not going to take off points for that, as long as you end up with the correct number of significant figures at the end.
Okay, good deal.
Yeah. Right. Oh yeah, and then we still have T final minus 25.0 degrees C. Now we have T final minus 25.0 degrees C. Oh, right, I was going to mention something about, right, so we flipped these units, or we took this, joules degree C, we divided, so that inverts it. So joules is on the bottom, the joules cancel, we end up with degree C as our units here. And now we can subtract 4.2117 plus, right? We add 25 to both sides, plus 25. Our final temperature will be 29. And again, let's look at our significant figures here. Looks like it's 3. 29.2 degrees C as our temperature final. Oh, and then there's just a blank page there. All right, so that was the last example. That is chapter 3. Are there any questions? Does anybody want me to go back to anything? I can hang out, or we can just call it a day. I will do the I will be doing a Discord watch party for the lab today. So I think that's lab 1 at like 2 o'clock.
So for the math, what would you recommend for getting some practice with the math? Because I'm probably gonna need to do some practice problems.
Oh, practice with like the algebra and
Yeah, exactly.
I would
It's been a really long time since I've done algebra, so
yeah, like I said, the back of the book has some stuff. Let me see if I can.
Yeah, those flowchart things, whatever they call this. I mean, it's like I always get lost. That's the hardest part for me here.
Yeah, so there's this appendix. You can see my research advisor is calling. I'll call him back though. So you can go through, like it takes you through basic algebra using, this is the ideal gas law equation. I would go through those. I would, look up the YouTube video from Khan Academy for algebra, run through those. I don't know if there are, oh, here's some practice problems. Or you could just take,
perfect.
yeah, so you could take these, run through those, and right, so like, even with these problems, it says solve for V2, but you could do this exact same thing and solve for V1, solve for P1. If you really want practice, try solving the equation for every variable. And
Okay.
I would use the conversion factors too, or for the conversion factors for temperature scales, because those have some addition and subtraction in them. Yeah.
All right. Thank you.
Mm-hmm. Anything else? Any other questions? Alrighty then. Yeah, if you have more questions later, hit me up on Discord, hit me up on Canvas, send me an email, send me a text, any of them. I'm never going to be mad to get a text from you guys, ever, Why would I be mad about you reaching out for help? So, yeah, all right. So thank you for participating, and I will either see you guys at 2 or see you guys tomorrow. And I'll try to put the right time on the schedule this time.
Thank you.
Thank you.
All right. Later. And
The recording has stopped.